An exciting, ever fascinating world of chemistry. We're looking at a few concepts to finish up bonding. The first one is formal charge. Formal charge is defined as a means of determining a charge associated with a covalent molecule. Now, any natural correct molecule, the total charge should equal 0. And the way we find it is we take the number of valence electrons minus the number of bonds minus the number of bond electrons. So let's do an example of SO2. Look at the structure. Remember, SO2 is a resonance structure. We have double bond and single bond. So we'll look at one of these first, one of each. And for formal charge, we do each individual atom. So oxygen has 6 valence electrons. That one has 1 bond subtracted away. Has 6 unbound electrons, so it's a -1. You say, wait a minute, it's supposed to be 0. Well, the whole molecule is going to equal 0. So let's look at the next one. Sulfur also has 6. -3 bonds, 2 doubles, a double and a single. And then -2, so I get a +1 charge. And then look in the last one, 6 minus 2 minus 4, that's 0, +1 -1 and 0. The whole molecule has a 0 charge. Now, the only exception to this, if it's a polyatomic, then the formal charge will be equal to the polyatomic, okay? And we'll do some more of those in class. All right, so looking at bond, next thing looking at is called bond enthalpies. Bond enthalpies is defined as means of determining the enthalpy reaction based on the enthalpies of each bond in the reaction. This sounds complicated, but it's really not. In order to do that, we're going to look at page 326 in your book. I gave that in your reading. It's right there. That's page 326, listing of all bonding enthalpies. So we take a look at the problem. We have to balance it first. Trust me, that is balanced. All right, so first we're going to look at the carbon-to-carbon bond. If you look at page 326, that's 348 kilojoules per mole. Right now, we just work with a number. Because there's a 2 out front, we're going to multiply that by 2. Now we're going to look at the carbon-to-hydrogen bond. Carbon-to-hydrogen bond is 413 from the chart, but we have 6 times 2. We have 12 of those. And a double bond oxygen is 495 kilojoules per mole. We're going to multiply by 7. Now, when we do the product side, we're going to subtract. So we'll subtract a carbon to oxygen bond, which is 799. There's 2 times 4. There's 8 of those. And then a hydrogen to oxygen bond is -463. 6 times 2, that's 12 of those. So we multiply through. We get 696 for 2 times 3, 48. We get 413 times 12, 4956. 3465 for 7 times 495. -799 times 8 is -639, 6,392, and 12 times 463 is -5,056. We add and subtract those all through, we get a -2,831 kilojoules per mole. Remember, that means that's an exothermic reaction, releases energy, it's negative. That's my energy. My answer. We'll check this one, do this one in class. Now, the last thing we'll look at is called molecular orbital theory. This is a different way to look at it, covalent bonding. We're looking at what's called VESPER, which stands for valence shell electron pair repulsion theory. That's what we've been looking at. Molecular orbital theory, or MO, is a different approach. To do that, we have to look at some values. We have what are called either single bonds, sigma bonds, or pi bonds, double bonds. We also have what are called unstabilizing bonds, or anti-bonds. And in order to see if the structure is correct, we generate what's called bond order. Bond order is the number of bonds minus the number of anti-bonds. So let's look at an example. Okay, when we do this, we set up a structure like this, and you'll have to, I'll give that to you on the test, so you don't have to worry about it, okay? We take the number of valence electrons. Chlorine has 7, and chlorine has 7. So a total of 14 valence electrons. Okay, so we put the first electron in to the sigma, second electron into sigma. Then we put the sigma anti, which is star, sigma this asterisk, and the 4th one. Then the 5th one, the 6th one, the 7th one, the 8th one. We put them in pies, we put them separately. 9th one, 10th one, and if it's okay with you, I finish the last ones, 11th, 12th, 13th, 14th. We're all out of electrons. Now we need to identify the bond order. Remember, so bond order is the number of bonds minus the number of anti-bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8 bonds. And we have 1, 2, 3, 4, 5, 6 anti-bonds. So 8 minus 6 divided by 2 is 1, so the bond order is 1. Now the question is, that's my VSPER. If I was doing valence shell electron repulsion theory, that's what we end up with. And the question, does it agree with Vesper? Well, we have a bond order of 1 and we have a single bond, so the answer would be yes. All right, now, the last thing we can look at, we'll look at this one, do this one class, and we'll do this one in class as well. All right, last thing we'll look at is either being a paramagnetic or a diamagnetic bond. Because Vesper, the English electron pair, doesn't deal with this, is only dealt with in terms of MO theory, we're going to look at this. So a paramagnetic is a bond that has a metallic characteristic. Diamagnetic has no. If we go back to the example we have, it's only paramagnetic having character if we have open spots for electrons. So in pi bonds or anti-bonds, we'd have to have one open here. Or if it was a sigma was the last one, we'd have to have one open here. But because this is completely full, this would be a diamagnetic bond. We're going to go over these all again in class. Any questions, let me know. We'll discuss it. Take care. Be good. Bye.